Hi, welcome to another edition of Easy Theory. So today we're going to do a quick summary video of closure properties for all the different types of languages that we talked about, as well as all of the problems that are the acceptance problems, the emptiness problems, the equivalence problem, and the all problem for whether those languages are decidable or not decidable. So let's do the closure properties first. So we have regular languages. Are they closed under union? And the answer, of course, is yes, because of the product construction. Intersection is the same story. You just change what final states you got. For concatenation and star, the answer is actually yes for both, because we were able to use the NFA, glue the two NFAs together, and then convert it back to a DFA. I'd really love to know if there's a way to do it directly with DFAs, and I don't know the answer. But you can actually just use a regular expression, and that works just as well also. For a complement, this was also a yes, because we can, if you had a DFA, you can actually switch which states are final and non-final. This doesn't work directly with NFAs, and there may be a way to do it with regular expressions, and I don't know. But with DFAs, you can certainly do it. All right, for context-free languages, for union, the answer was yes, because we can just take the start variable for both of the grammars that we got. For if it was L1 union L2, I get the grammar for L1 and the grammar for L2, look at the start variable for each, and I make a brand new start variable that goes to the union of the two original start variables. There's some more to that, but that's the basic idea. For intersection, the answer was, in fact, no, they're not. And the reason was that if we had the language a to the n, b to the n, c to the different variable, and the other language being a to any variable, b to the n, c to the n, then the intersection of those two languages is a to the n, b to the n, c to the n, which is not context-free. And the original two languages are context-free, so it's not closed under intersection. For concatenation and star, the answer was yes. I'm going to switch to green. The answer was yes, because we can do that same trick with the two start variables. So this time it has the new start variable going to S1, S2. And for star, what you can do is have it go to S1, then concatenated with the new start variable, or epsilon, because epsilon is in the star of every language, and it's basically like the NFA star idea, which is you go through the grammar once, so that's why S1, and then S, which is the new start variable, you can go back through if you wanted to go again. And for complement, the answer was, of course, no, because the complement of A to the n, B to the n, C to the n we saw was context-free. For decidable, the answer is yes for union, because I can just run the two machines, because I guarantee they both run in a finite amount of time, and I just run one, I run the other one, and I say yes if at least one of the two said yes. And the same is true for intersection. For the same reason, except now you just accept if both of the machines says yes. For concatenation, the actual answer is yes. And the idea is that you're asking if the first piece belongs to the first language and the second piece of the string belongs to the second one. And you don't know what split it is, so what you do is you go over all possible splits of the string into two pieces, and you run the first piece on the first machine and the second piece on the second machine, maybe with a multi-tape or something, and you accept it. If there is a way to split it so that both of the two parts accept, then we accept, because now we just found that one piece belongs to the first language and the second piece belongs to the second one. If you try all possible splits and none of them work, then there's no way that the string could have been the concatenation of two strings, one from the first and one from the second. And for similar reasons, they're closed under star too, because you just try all possible splits, including the empty string, and there are ways to handle that so that you only have finitely many combinations. I'm not going to show that here, but there are only finitely many combinations you ever need to consider, and you just try all of them. And if any one of them accepts, where each of the string pieces belongs all to the same language, so the decider says yes to all of the pieces of the string, then it's in the star language. Or if the string is epsilon, that's another thing too. And for complement, the answer is yes. And because we can actually just swap the Q accept and Q reject state in the machine, because I know I'm going to hit one of the two states, one of those two, because I know the machine is a decider. It always will hit one of those two. So I can just swap which one is an accept, which one's final, reject. For recognizable, it's a little harder, but the answer is actually yes for union. And I can't just run the first recognizer on the string and then try the second one, because the first one might run forever. So what you do is you run each of the two machines for one step each, and then if either one ever accepts, then we accept. And if both of them run forever, it doesn't matter, because if both of them run forever, then it's not in the union, and then therefore we are not required to do anything with that string. So, and similar reasoning for intersection, except now if both of the two machines happen to say yes at a given point, or half of them say yes at any point, then we will accept. It's a similar idea. Actually, for concatenation and star, it's very, very similar too. It's actually a green check mark for both. Because for concatenation, you try all possible splits, but you do them at the same time by running each one of them for one step, so that you never have the possibility of one of the steps taking an infinite amount of time. So if you do each one of them for one step, and you just keep going back and forth, doing the same thing over and over, then you're guaranteed to, if it will ever accept, then you will hit it at some point. And the same idea is for star. You try all possible splits, but you do them at the same time, one step at a time, instead of just running one to completion and then going to the next one. For complement, though, the answer is in fact no. And the reason is that ATM is undecidable, but is recognizable. And so I'll actually explain that a little bit more. So ATM, which I have covered on the channel, but not in a recent video. So ATM is undecidable, but recognizable. So it is recognizable. And there's a result that I haven't proved on the channel yet, that if L is decidable, actually, I'll say it this way. L is decidable, a language L is decidable, if and only if it is recognizable and its complement is recognizable too. So this tells us that if the complement of ATM was recognizable, then ATM is recognizable, the complement is recognizable. That would imply that ATM is decidable, but that's not true. So it is recognizable, but ATM complement is not recognizable. So that means that recognizable languages are not closed under complement. And so this is just a little summary table of the main closure properties for the languages we talked about. The glaring omission here is, what about deterministic context-free languages? Which operations are they closed under? And put what you think about them in the comments down below. All right, so the other thing I wanted to discuss here is, for the different types of models, we talked about certain types of problems, like the acceptance problem and the emptiness problem and the equivalence problem and the universality problem, called the all sub whatever problem. So we have DFAs and NFAs and regexes being in the same class because they're just all equivalent to each other. We can always convert from one to the other. So I'm going to make a little table here. We had CFGs and PDAs, because those are equivalent to each other. And we had linear bounded automata, although I haven't talked that much about it on the channel yet. I'm going to talk more about that in the spring. And we had Turing machines. So the main problems that we talked about are the acceptance problem. So I'm going to abbreviate that as A sub x. And what I'm going to put in this cell right here is whether A sub DFA or NFA or regex is decidable. Here I'm going to put whether it's decidable. For A CFG, A sub PDA, same thing. A sub LBA, I'm going to put whether that's decidable. ATM, whether that's decidable. And similarly, for the emptiness problem, I'm going to put like that. The equivalence problem, I'm going to put like that. Actually, I'm just going to do those three. The universality problem is actually, in some sense, the same as the equivalence problem, but I'm not going to talk about that. So I won't talk about that. Okay, what about the A sub DFA problem? We saw that that was decidable because we can just simulate the DFA. E sub DFA is decidable because we can just check whether or not we could reach a final state at all, and it's equivalent to that question. The EQ sub DFA problem is decidable because we can set up a DFA that accepts exactly the strings that one DFA accepts and the other one does not accept. And if that set of strings is empty, then there's no string that one DFA accepts that the other one doesn't, and then therefore they are equivalent. The DFAs accept the same language. For CFGs, the A CFG was decidable because we can just run all strings of length 2n minus 1 essentially, and that's only a finite amount of work. The ECFG problem, we had to introduce this idea of productive variables, but that's essentially the same idea as what we did for Chomsky normal form, and that takes a finite amount of time too because there's only a finite number of variables and rules. I'm going to skip EQ. The A sub LBA problem is decidable. I've done that way long ago on the channel, and what you do is you just run the machine long enough to where you guarantee you have repeated a configuration, and then therefore you know at that point the machine must run forever, so you immediately reject. But unfortunately, every single other box here is undecidable. So the ATM problem I've done on the channel. The ETM problem I will eventually do, and there's a way to show that it's undecidable in multiple ways. But one way is to use Rice's theorem, which I have done on the channel innumerable times. Another way is to suppose it is decidable. Then you can show that ATM is decidable, but that's not true. EQTM is undecidable. In fact, it's not even recognizable either. But it's not decidable because if it were, then you can solve the ETM problem, and we know it isn't decidable. So EQTM is undecidable. E sub LBA is undecidable, mainly because of using something called computation histories. And it's a kind of a complicated proof, but I've done it once on the channel, and what you do is you set the LBA up to accept any string that could possibly be a computation history. Then you assume that you can solve this problem. Then you can solve the ATM problem because given the Turing machine M and W, then there's only one possible computation history that could ever be accepted. So if M accepts W, then this LBA will accept one string, and if it does not accept W, then this LBA will accept nothing. So the test of whether that LBA is empty or not is equivalent to asking whether a Turing machine accepts a given string W. And so this is undecidable. And EQ LBA is undecidable for the same reason as it was for Turing machines down here. If this was decidable, then this thing would be too. But it's not. EQ CFG is actually undecidable, and that's a kind of a more complicated proof, but it's similar to this one, where instead of, so I mentioned the universality problem, so it might be worth mentioning here. So all sub x means we can figure out whether or not that model accepts sigma star exactly. So figuring out whether a DFA has language sigma star, that's definitely decidable. It turns out that this is undecidable for context-free grammars. And the reason is that we build a CFG that accepts all strings that are not computation histories. And so given a Turing machine M and input W, then the CFG that we have will accept sigma star if M does not accept W, and it will not accept sigma star if it does accept W. And so the question of right here in this part right here is the equivalent to the ATM problem in terms of undecidability. So then for the EQ problem, it's equivalent to the all problem for undecidability purposes, because suppose that we can solve the EQ problem, then what we can do to solve the all problem is, given a single CFG and I want to figure out whether it accepts sigma star, then I build a different CFG that does have sigma star, and I run the EQ test on it, and then that's equivalent to the all CFG problem. And so EQ CFG is undecidable for that reason. All right, so that was a quick summary of closure properties as well as decidability and undecidability results. So hopefully that was interesting. Leave thoughts about either one of these in the comments down below. As always, please like the video and subscribe to the channel. It really helps us out. There are many other links in the video description if you want to support the channel further. And as always, I'll see you next time.